Welcome! In this video I talk about vectors. Vectors are dynamically allocated arrays which own the memory allocation. They are one of the most versatile data structures out there and are very similar to the vectors offered by the standard template library in C++. I start by showing you some examples how you create vectors and how you use them. For example, here I create a mutable vector of U64s, and I just use the new constructor. Note that I don't have to import anything. The vec template is always available. Since it's mutable, I can push to the back, just push values at the back, and I can print elements of vectors and access them like here. And again, I need the debug notation to print the full vector. Let's see how this works. Here, you see the two elements, 1 and 2, and the whole vector. As in C++, vectors have a capacity and a current length. If you know beforehand that you need more elements in the vector, like for example here 3 elements, I can allocate the vector with capacity. In this way here, and then I don't get reallocations when I push as many elements there. Furthermore, you can here see the member functions len to see the length of the vector and the capacity. And if I run this, you will see that this vector has length 2 because I push 2 elements and capacity 3. Having said that, that means the with capacity constructor with an argument constructs a vector which is empty. It has 0 length, but it has the capacity I specify here. The next thing I show you is the vec macro. In this way, you can create a vector directly from some values. We'll talk about this in a second. But let me first show you about bounds checking. This vector has 3 elements, so the indices are 0, 1, and 2, because it's 0-based. So if I access element 3, I'm out of bounds. Let's see what happens if I run this. If I run this in debug mode, then I get an index panic because the index is checked and I access outside the bounds. Note that if I do this in release mode, I also get a bounds check. So bounds check in vectors are always done. In a mutable vector, you can just assign individual entries like this here, as you would expect it. And if I run this, you can see that the second entry here is changed from a 2 to a 12. The vec macro is more versatile than you have seen. You cannot just list all the values, but you can also specify a single value and repeat it multiple times with a semicolon notation, like here. So these are 3 17s, and these are 4 U32 17s. Notice that this integer literal has the type built in. So these are 32-bit types. Therefore, I don't have to specify the type here. Whereas if I specify the type, I can use just plain integers without specifying the type. Let me run this. It works. We can also conveniently iterate over vectors. Here I have a vector of 3 U64 integers. If I call the member function iter, I get out an iterator over this vector. That means if I run a for loop like this here, x will have the type of a reference to a U64. Therefore, I can just print it like this in the loop. Let me run this. Indeed, it prints the values 1, 2, 3. Note that I can also use the notation to just say for x in v here. Notice that x is then of type U64. Why is that? Because this is the notation for the longer into iter call, which consumes the vector. So with into iter, we transform the vector into an iterator such that the vector is afterwards gone, and therefore the very elements are moved into this x loop variable here. Therefore it's an actual value u64. That means that if I try to print the vector, or access even, after the loop, the compiler will be unhappy with me because it says it's a borrowed value v which has been moved away. So here I would borrow it after it has been moved away, and has been moved away because of this inter itu. That means the shorthand notation for x in v is equivalent to into iter, whereas the shorthand notation for x in reference v is what we had before for iter, and then I can use the vector afterwards. I can also use a simpler notation for mutable access. Here I use this notation here to iterate with x over the vector. Now x is a mutable reference to u64, and then I can use the star x notation to actually mutate the vector. So this will mutate every element of the vector, as you can see when I run it. I should mention that this notation here is equivalent to calling itermut or itermutable here. So this will also compile and work. I will conclude this video with slices. Obviously you can take slices of vectors with a slice notation, like this here, either where the upper bound is not included or where the upper bound is included. So w will be just the first entry, and u will be the first two entries, as you can see here. Finally, let me show you mutable slices. Here I form a mutable slice or a mutable reference into a vector. And this shall show you that you have the same borrowing rules as before. Here the compiler notices that w, the reference to the first element, or index 1, is only used from here to here. So therefore, it let you borrow in a mutable way from here to here afterwards. If I would move the print down here, the compiler would not be happy because it would say that here we are doing an immutable borrow of something which is borrowed already. Namely here, we cannot borrow v as mutable because it's still borrowed as immutable reference. And the same holds for slice borrows. But this way, it compiles and runs. There would be lots more to say about vectors, but I think you can read up in the excellent documentation. I provide links in the associated webpage. For now, this was it. See you in the next one.